Hello and welcome to Today I Learned Climate, the show where you learn about climate change from real scientists and experts. I'm your host, Laur Hesse Fisher, with the MIT Environmental Solutions Initiative. We're back with our next episode in our series on energy and climate in partnership with the MIT Energy Initiative. So far this season, we've talked about ways our electricity system could burn fewer fossil fuels so that the carbon that's trapped in oil or coal or natural gas stays underground, where it can't warm our atmosphere. But today, we'll be talking with two members of the MIT Energy Initiative about a technology that actually doesn't try to replace fossil fuels.
My name is Howard Herzog. I'm a senior research engineer in the MIT Energy Initiative. In about a month's time, I'll be celebrating my 30th anniversary at the Energy Initiative, or its predecessor, the Energy Lab.
I'm Brad Hager. I'm a professor of Earth, Atmospheric, and Planetary Sciences. And in addition to being a professor, I'm the co-director of the MIT Energy Initiative's Low Carbon Energy Center on Carbon Capture, Utilization, and Storage.
That's right. They both work on something called carbon capture, utilization, and storage, abbreviated as CCUS, or sometimes just called carbon capture, like we'll call it today.
The problem for climate change is the emission of CO2 into the atmosphere. So when you burn fossil fuels, you create CO2. The idea in carbon capture is that CO2 that's created by the burning of fossil fuels, you stop from going into the atmosphere. And you do that by capturing it, and then you put it somewhere other than the atmosphere.
So why would we even consider this? Well, as we've heard earlier in this series, adding clean energy sources like solar, wind, and nuclear comes with a lot of complications that we need to work out. In theory, carbon capture lets us use the energy system that we have now, but removes the CO2 emissions from that system.
The problem with climate change isn't fossil fuels. The problem is the buildup of greenhouse gases in the atmosphere. And so what we want to do is look at solutions that reduce the amount of greenhouse gases we're putting in the atmosphere. If we do that by using less fossil fuels, which I think is going to be part of the solution, so be it. But it doesn't mean that we can't continue to use fossil fuels if we have the technology to use them without putting their emissions into the atmosphere.
So today we'll be diving into how carbon capture works, what we're supposed to do with all of this CO2 once we capture it, and just how realistic this is as a way to help slow climate change. But let's start with the basics. Because power plants and factories emit so much carbon dioxide in one place, most carbon capture happens there, from the flue gas that comes out of their smokestacks. Here's Professor Hager.
The method of capturing carbon dioxide that has been used for the longest is to run the flue gas through a solution of chemicals called amines. The carbon dioxide dissolves in the amines.
Then you compress it to turn it into basically a liquid, a high-pressure liquid. Technically, it's called a supercritical fluid, but it basically acts like a liquid. And then you can put it in a pipeline, and you can put it down a well into the earth. And the place that right now is the biggest opportunity to store the CO2 is in deep underground formations.
Engineers look for just the right places to do this so that the CO2 can't leak back into the atmosphere or into our groundwater.
So we can think of a good reservoir candidate for storing this stuff as being a layer of shale called the caprock to keep the fluids in place, and then underneath it a layer of sandstone to provide empty space to put the CO2 in.
Originally, I imagined these underground caves that the fluid CO2 was poured into, but actually it's injected into a rock, which kind of absorbs the CO2.
The way to think of it is think of you're at the beach and you have a bucket of sand and you can put water into it and the water goes in the pores between the sand.
The CO2 then sits there. in the same way that oil has been sitting in these kinds of spaces underground naturally for millions of years. And if this sounds like science fiction, well, actually, it's already happening. There are around 20 facilities using carbon capture and storage around the world, although most of them aren't power plants. They're other industrial plants like natural gas processors or steel or fertilizer plants. And some of them have been running for a long time.
The first really serious project is called Sleipner, run by the Norwegians. So in 1996, they started producing sour gas, cleaning it up, removing the carbon dioxide, and injecting it into the subsurface underneath the North Sea. And for the last 23 years since the plant started, they have been injecting about 1 million tons of carbon dioxide a year into the subsurface.
1 million tons of CO2 is about the same that 200,000 US cars emit in a year. But burying this CO2 is not our only option for dealing with it.
Recently, there's been a lot of interest in using the carbon dioxide as an intermediate product. It can be used to make plastics, make feedstocks for plastics, and it can even be combined with hydrogen to make, for example, jet fuel.
The more useful stuff we can make out of CO2, the more reason that companies will have to capture it. Because right now, there isn't really a big market for this captured CO2.
At best, it's going to be a niche solution. The amount of CO2 that we are producing from energy use basically is so much larger than markets for a lot of the products people are thinking of. You're still going to need to put it in underground reservoirs of carbon capture, and it's going to be adopted at large scale.
What does large scale really mean? Well, let's imagine that we only capture and store 1/10 of the CO2 that we're emitting today. That would be about as much liquid as all of the oil consumed worldwide. And oil is a massive industry served by huge tankers and storage depots and hundreds of thousands of miles of pipelines. It would take a lot to repurpose or build new infrastructure for moving around CO2. And if you're a power company or a steel manufacturer, you might be wondering why you would pay for it. Which brings us to one of the big challenges for carbon capture. It's pretty expensive.
There's additional expense that you need to build the facility to do this, and then it takes energy to do it. So the increase in cost of electricity coming down the power line to the consumer is on the order of 30 to 50%.
And at the moment, there's not much of an incentive for power companies to take on that extra cost.
In order to promote the capture of carbon dioxide, you need some sort of economic incentive to do that. So you can have a carrot or you can have a stick. And the carrot, which is being held out right now, is the basically tax rebates.
Yeah, actually, here in the US, we offer companies a tax credit for capturing their carbon emissions. Right now, it's about $50 per ton of CO2, but it's not really high enough to retrofit all of our fossil fuel power plants. So that's the carrot. And the stick?
The other side is putting a price on carbon. And so if that's high enough, a company will voluntarily capture and sequester its carbon dioxide.
We did a whole episode on carbon pricing in our first season, so check that out to understand how a carbon price would work. The thing that you're hearing here is that capturing and storing CO2 at our current power plants is possible. But we either need to decrease the costs of doing it or increase the incentives. The policies that we choose can make a huge difference to companies deciding whether or not to invest in something like carbon capture.
Technology doesn't happen in a vacuum. Innovation doesn't happen in a vacuum. You need to create the markets, and that's a political thing. And see, I think if you had a carbon tax, it will create innovation. And there's a lot of room for innovation in this area. But there's no silver bullet in dealing with climate change. There's no one solution that's going to provide the answer.
If it becomes cheap enough, carbon capture could be a long-term solution for many power or manufacturing plants. Or its role could be to help us cut emissions immediately until we solve the challenges with wind, solar, and nuclear power or energy efficiency.
I see this as a strategy that will bridge through the next 3 decades. So the next 20 to 50 years, I hope that cheaper sources of electricity, of clean electricity, will be developed.
So carbon capture is one more tool that we can add to our clean energy tool belt. And it's just like all the other technologies we've explored in this series, in that it's powerful, but with its advantages and disadvantages. And none of them are able to do the job on their own. There is a lot more to learn about carbon capture. We've left some links in the show notes and on Twitter to places where you can learn more, including a couple of episodes of the MIT Energy Initiatives podcast, which does a deeper dive. Next up on TIO Climate, we're looking at fusion energy, so stay with us. A quick shout out to Amy Lee Wee, who left us a review on Apple Podcasts. Amy Lee Wee says, super informative podcast that breaks down really complex topics into small bites and does so without placing the blame. Keep up the good work. Thanks, Amy Lee Wee. We appreciate it. We invite you to leave us a review on Apple Podcasts as well, or wherever you're listening from today. Today I Learned Climate is brought to you by the MIT Environmental Solutions Initiative. Thank you to Brad Hager and Howard Herzog for talking with us, and thank you for listening.